This is Dr. Sweeney, and what I'm going to be doing right now is I'm going to be going over the second part of the exam review for chapters 2 and 3, the discussion questions that we had taken a look at earlier. What I want to remind you of is in many cases, there's not just one way of going about solving these things. In fact, or in terms of explaining your reasoning, all right? Because what we're looking at is mathematics, and in particular, we're looking at linear algebra. There's a lot of different ways to approach not only different kinds of problems, but also different kinds of concepts. And so I'll go over, maybe one or two for each one, but you should realize that you want to be somewhat flexible. Flexibility is actually a really important thing in terms of linear algebra. It tells you how much you actually really do know. Okay, so let's start out. We're going to take a look at this question. This, so let's look at number 8. Number 8 starts out with giving us a solution to a system of equations, ax equals b, in vector form. So it says x equals t times negative 1, 1, 1, 3, plus s times negative 1, 0, 0, 1, plus 5, negative 1, 2, 0. And then it asks us, what I'm asking first is to give a single solution to ax equals b. And all this means is just give me a particular solution, one value if we selected values for s and t. So x, let's let s equal 1, and we'll let t equal 1. Okay? Then x is going to equal 1 times negative 1, 1, 1, 3, plus 1 times negative 1, 0, 0, 1, plus 5, negative 1, 2, 0. When we add those all together, I'm going to get negative 1 plus 5, that equals 3. 1 plus 0 plus negative 1 is 0. 1 plus 0 plus 2 is 3. 3 plus 1 is 4, plus 0 is 4. And there is your single solution. Simple. Just a matter of understanding how to read it. Okay? Now, what is the geometric representation of the solution? All right. If I look here, so this solution here has one free variable, two free variables. Okay. This variable, this vector right here, okay, or that column vector is actually, it's like a y-intercept. It actually tells you where this particular geometric object is passing through inside of the plane. It's not actually a part of its geometric representation. We're only going to be looking at the free variables. And so those free variables, right, there are two of them, right? So two free variables indicates a plane. And so that's a plane, a plane. And that's it. It's a plane. One free variable, that's a line. No free variables, it's a point. Three free variables, you have what's called a volume. And four or more free variables, you have a hypervolume. Okay, now how many free variables are there in the solution to ax equals b? Two of them, t and s. Two of them, t and s. Okay, great. That's it. Now, suppose that a is 4 by 4 is a invertible, right? And then we want to think about an explanation for this as well. So let's suppose that we have this solution right here to ax equals b. It has two free variables, all right? So if a is 4 by 4 and it has two free variables, that tells me something about the matrix, okay? So we're going to look at this and we're going to say, okay, so a, well, let's say ax equals 0 has two free variables because ax equals b has two free variables. All right. So the number of free variables that we have uh, inside of a system, okay, is really dependent upon the coefficient matrix. So if the coefficient matrix if ax equals 0 has two free variables inside of it, then every ax equals b, if it has a solution, will have two free variables as well. All right. On the other hand, if ax equals 0 has no free variables, right, that it has a unique solution, right, then what we end up with is we're going to end up with, if there is a solution for ax equals b, we'll end up with a unique solution for that ax equals b, right? So the number of free variables is consistent and it's dependent only upon a, right? So we've got ax equals 0 has two free variables, right? We know that a is 4 by 4, okay, right? And so if ax equals 0 has two free variables, then ax equals 0 has an infinite number of solutions. By the invertible matrix theorem, then, A is not invertible. So remember, the invertible matrix theorem has a set of equivalent statements. So if one of the statements is true, then all of them are true. But it actually goes the opposite way as well. If one of the statements is false, then all of the statements is false, right? Because they're actually equivalent. So in this case, we have ax equals 0 does not have the trivial solution. And since ax equals 0 does not have the trivial solution, A is not invertible. All right. There's a lot of other ways to look at this too. Since A has two free variables, we could actually say that A only has two pivots. All right, or the row reduction of A only has two pivots. And since the row reduction of A only has two pivots, the rank of A is 2, right? For A to be invertible, the rank of A would need to be 4. Right? So that's another way to look at it, right? We've got several different ways to look at the same problem. Now, next step. Suppose that A is 4 by 4. What is the rank of A? See, we just talked about that. All right. So now what I want to imagine is I'm just going to kind of like picture a matrix that I have here. A equals, okay. And what I've got, it's 4 by 4, and it's got two free variables. So let's let this one x3 be free, okay, and x4 be free. Now what I know, if x3 and x4 are free, that means that there are no pivots in x3 and x4. Okay, there are no pivots in x3 and x4, so I'm going to place my pivots in x1 and x2. All right, and then I'm just going to pretend this is going to be RREF of A. This is my row reduction. It's going to look like that, and then that means that I've got rows of zeros down here because free variables means no pivots. Okay, so I got like -1, 2, 3, 5, something along those lines. Who knows what it looks like? But what I definitely know is that because these two are free, there are no pivots. So consequently, rows 1 and 2 have pivots, and then everywhere else has got to have zeros inside of the row reduction. Okay? By this look, okay, we get that the rank of A equals 2. Now, there's also a theorem in your book that says that if you take, excuse me, the number, here's the theorem in your book. It says basically this. It's got the rank of A equals, okay, the number of columns minus the number of free variables. Which makes sense, right? You've got X number of variables, okay? Like in this case, you've got 4 variables, right? What you do is you say, okay, well, 2 of them are free. That means that 2 of them are not free, okay? And since 2 of them are not free, right, we end up having those are going to be the ones that are defined, right? That we're going to end up with X equals something when we actually go out and find the parametric solution. When we find the parametric solution, okay? And so consequently, what we get is we get that 4 minus 2 of the free variables, number of columns 4 minus the 2 free variables gives me the rank of A. There you are. So now here's question number 9. So suppose that A is 4 by 5 and it has one free variable. Is AX equals B consistent for all B? So what I want to do is I want to sit down and I want to say to myself, okay, so I'm going to imagine this matrix. It's 4 by 5. Okay. So it's got 4 columns, right? Excuse me, 4 rows and 5 columns. 2, 3, 4, 5. Okay. And so that's my look. And it has one free variable. So this one here is going to be my free variable. Okay. Free. Right. Here's my free variable. So for each one of these other variables, x3, x1, right, x2, x3, and x4, I've got to have a pivot because they're not actually free. So 1, 1, 1, and 1, right? Because by definition, right, that's what it means to be in the row reduction. Okay, so like that, they'll make this RREF of A. So all right, and that's RREF of A. Okay, well, now let's look at this. Well, if I have AX equals B, right, my row reduction of A is always going to look like this, okay? So the row reduction of A is unique, okay? And it doesn't matter if it's B on the end of it or if it's 0. And it does not matter if we're looking at AX equals B, AX equals 0, or just A, or just RREF of A, right? We're going to still get that the row reduction is going to remain the same. So imagine what it looks like to have a row reduction that looks like this. 1, 2, 3, 4 pivots, right? Plus a free variable. So you have no rows of zeros, right? Since there are no rows of zeros, in RREF of A, we will not get any inconsistent systems. Remember that to have an inconsistent system, we have to have rows of zeros, right? A row of zeros instead of the row reduction, to get like 0 equals some value. 0 equals 1 oftentimes when we row reduce. So in this case, we're not going to get 0 equals 1, right? Because there's no row of zeros in that row reduction. So consequently, no inconsistent systems. Thus, A is consistent. AX equals B is consistent for all AX equals B. Now, be very, very careful. This does not mean that AX equals B has a unique solution. In fact, what you're going to get is you're going to get an infinite number of solutions for every B. So like for every value B, right, you end up having an infinite number of solutions because you've got this free variable. But are you going to get a consistent system? Yes. Consistent system means at least one, right? So I've got at least one solution to AX equals B. So consequently, this is a consistent system. Just is not unique. Very important. So number 10 says, give an example of a row reduction of the matrix A that has a rank of 4 and 2 free variables. Then write the solution to AX equals 0. Okay. Now, what we're going to say is okay, so I've got to think about what's going on with this matrix, right? It's got a rank of 4. So rank of 4 rank of A, equals 4 means 4 non-zero rows. Or 4 pivots would be another way to look at it. So you've got 4 non-zero rows, at least 4 pivots. Okay, well, 4 pivots exactly. Then you have 2 free variables. So what this means is that if you have 4 non-zero rows, 4 pivots, right, plus 2 free variables, this one has 6 variables in every system. So minimally, what we've got to have, right, okay, is we've got to have something that's 4 by 6, right? Because you got to have 4 pivots, 6 free variables. Could you have more? Yeah, you totally could. You could have it be 6 by 6, That would be totally fine too, right? But what you want to get is that if you are going to have these 4 pivots and 2 free variables, the number of columns you have has to be 6, right? To represent that you have 6 variables in each one of the systems. So I'm going to draw that. So I'm going to create an example of this one. I'm going to make mine 4 by 6, okay? Because why not? So here's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1, and then I'll now put my 2 free variables. Let's do 1, -1, 0, 1, 1, 0, and -2, 1. Why not? Right? And so that's the example, okay, of the RREF of A. Let me take a look. I've got 4 free variable. I have 4 pivots. 1, 2, 3, 4. Okay. The rank of A is 4 because I have 4 non-zero rows, and I've got 2 free variables. Done. Okay. Now, what I want to do now is to say, then write a solution to AX equals 0. All right. So let's do that. What I'll do is I'll first parametrize it. So x1 plus x5 minus x6 is going to equal 0. Okay. x2 plus x6 will equal 0. X3 plus x5 will equal 0. And then x4 minus 2x5 plus x6 will equal 0. And then, so what we'll do is now we'll let we're going to state first that x5 is our first free variable. We'll let that be s, and we'll let x6 equal t. Okay, just create any variable that you'd like there. So x1, right, what we'll do is we're just going to move over x5 and x6 over to the other side. So x1 is going to equal negative x5 plus x6, excuse me, plus x6, which is simply equal to negative s plus t. x2 will equal negative x6, which equals just negative t. x3 will equal negative x5, which equals negative t. x4 will equal 2x5 minus x6, which equals 2s minus t. Great. And so that's a parametric solution to ax equals 0. If I want to write it as a vector, I'll let it be x, okay? And then what I'm going to do is I'm going to line up all my s's, all right? So this first one is going to be s, that's going to be my scalar. And in the x1 term, I have a negative 1s, right? This one right here, that's negative 1, excuse me. Then in x2, I have no s's. In x3, excuse me, this was wrong, it's not negative t, it should be negative s. In x3, I have negative 1s. In x4, I have 2 s's. x5 is s. And x6, there's no s's, there's just a t. Then plus t, and now I'm just going to line up all my t's. So I've got 1t in x1, negative 1t in x2, 0 xt's in x3, negative 1t in x4, 0 in x5, and 1 in x6. And so that makes that my vector solution. Okay? So what this is it's a visualization issue, a visualization problem, right? Knowing that when we have the rank, okay, of a matrix, A, that tells me how many pivots that I have inside of that matrix, how many non-zero rows, which equals the number of pivots. What is a free variable? They have to represent the other variables, right? So each pivot represents one of the variables in the system, and the other 2 pivots, the free ones, excuse me, the free variables represent 2 more, right? So what we have here is 4 plus 2. We have 6 variables in the system. So minimally, the number of columns is the number of variables in the system. So I've got to have 6 here, okay? And then I can have as many rows as I want, as long as it's more than 4, right? Because you've got to have 1 row for every pivot. All right, so suppose that the following is A represented as a series of elementary matrices. And so we have A, and it's actually a product of elementary matrices. is M1 times 1/2, so it's that multiplication one, times A12 negative 2, times P23 times M3 negative 1, times A23 1/3. All right. So what I'm trying to get out here is do you understand how elementary matrices work, right? And then how does that relate to things like the determinant and the inverse? All right. So this first asks us, what is the determinant of A? All right. So we know the determinant of A, okay, is going to equal the determinant of all these guys, right? M1, 1/2 times A12 negative 2 times P23 times M3 negative 1 times A23 1/3. All right. We just want to get that these matrices, this is a multiplication matrix, addition, permutation, multiplication, and addition. All right. And this is going to equal just the determinant of M1 1/2 times the determinant of A12 negative 2 times the determinant of P23 times the determinant of M3 negative 1 times the determinant of A23 1/2. And that's one of those things that you can do because, well, it just turns out that that's how determinants work, right? It's one of those things that we proved. So now what I want to get is that, so that's what determinant A is equal to. So determinant of M1 1/2 is going to equal 1/2, right? So you want to go back, oh, that's right. It's a multiplication matrix. It's going to just basically be the scalar times any addition matrix has a determinant of 1 times any permutation matrix has a determinant of negative 1 times multiplication matrix negative 1, okay, times an addition matrix, the last one here, which is just times 1. So this is now 1/2. So that's the determinant of A. The determinant of A equals 1/2. Yay. Okay, cool. Now, what is A inverse as a sequence of elementary matrices? So to find A inverse, I need to take, so A inverse is going to equal the inverse of all of these guys. M1 1/2 times A12 negative 2 times P23 times M3 negative 1 times A23 1/3. Okay, that inverse. Okay, now the inverse, when we invert a product of matrices, what we're going to do is we're basically going to invert each individual one and then switch their order. So this is now going to be A23 to the 1/3 inverse times M3 to the negative 1 inverse times P23 to the negative 1 times A12 to the negative 2 inverse times M1 1/2 to the negative 1, or inverse, whatever. Okay, so now this, all right, what we know is that this is the inverse of A23 1/3 is just going to be A23 to the negative 1/3. So you make each one of those values negative times M3 to the negative 1. So that's M3, and it'll be negative 1 over 1, right? So it'll be negative 1 over 1. So you actually take the inverse, or 1 over negative 1, excuse me. So you just flip it times the inverse of P23 is P23. Because if you switch 2 and 3, right, now 3 is in the 2 spot and 2 is in the 3 spot. So if you want to switch them back, just do the same thing. So that remains the same. P23 times A12 negative 2 is going to be A12 positive 2. Okay, times M1, and as I said before, we're just going to take the inverse of that, so it's going to be 2. All right, and that in fact is A inverse. Let me write these out just to give you a little bit of practice. All right, A23, if we've got a 3 by 3, okay, A23 is going to have, it's going to be 1, 0, 0, 0, 1, 0, 0, negative 1/3, 1. Okay, so in the 3, 2 spot, third row, second column, we're going to put negative 1/3 times, all right, so this one here is going to have 1, 0, 0, 0, 1, 0, 0, 0, negative 1 because we're changing row 3. Okay, multiplying it by a negative 1 times, this is P23, so this is going to be 1, 0, 0, 0, 0, 1, 0, 1, 0. We'll switch the second and third columns. A122 is going to be 1, 0, 0, and then this will be 2, 1, 0, because we're going to change the second row. First column is going to become a 2, 0, 0, 1, and then times, last phrase, wait for it. Okay, is going to be 1, or actually it's going to be 2, 0, 0, because we're multiplying the first row, 0, 1, 0, 0, 0, 1. All right, and there are our elementary matrices. And that is A inverse. How would you go find A inverse? You'd multiply all these together. Ta-da! Okay. So let's look at number 12. So suppose that A is 3 by 3 and invertible. What is the solution to AX equals 0? Okay, so A is invertible. By the invertible matrix theorem, the solution to AX equals 0, by the IMT, the solution to AX equals 0 is the trivial solution. Is to AX equals 0 is the trivial solution. So X equals 0, 0, 0, right? It's three-dimensional. It's an R3, right? So there it is. Now, what is the geometric description of the solution to AX equals 1, negative 1, 2, 1? Since A is invertible, right? We know that A is invertible. Well, we also know that that means that AX equals B has a unique solution for all B. Well, what is a unique solution for all B? I mean, like, what does that mean, right? Okay. Well, it means that there's only one. So every solution is what? It's a point. Okay. So each solution to AX equals B is a point. So the solution to AX equals negative 1, 2, 1 is a point. No free variables. What does it mean to be no free variables? It means that it's zero dimensional. Zero dimensional, what's zero dimensional? A point. All right. Finally, what is the rank of A? The rank of A equals 3 because of the IMT. All right. You can just go in. It's the invertible matrix theorem, right? The IMT will tell us that the rank of A is equal to the number was equal to n, right? Since A is n by n. And so since n is 3, there you go. Rank of A is equal to 3. So this question is actually just asking you, like, do you know the invertible matrix theorem, right? Can you tell me what specifically we get from these kind of results? All right, cool. All right, suppose that A is 4 by 6 and the row reduction of AX equals B is as follows. And so we're given this row reduction of an augmented matrix. Okay, write the parametric and vector solutions to the system. So I'll start out here. I've got x1, that's my first row, is equal to x1 minus 2x1, 2, 3, 4, 5, minus 2x5 equals 1. X2 is free. Since there is there's no value for that variable sitting there, that means that x2 is actually free. Okay, x3 equals, or x3, excuse me, plus x5 equals negative 1. X4 minus 2x5 equals 3. And then x5 is also free, right? And it's free because it doesn't have a pivot. So anywhere we don't have a pivot, we end up with a free variable. There's no pivot in x2, So x2 is free, right? And there's no pivot in x5, so x5 is free. And by the way, that just gives me x5. And I'll let x5 equal t. So we'll let x2 equal s, okay, and x5 equal t. So now x1 equals 2t plus 1. x2 equals s. x3 equals negative t minus 1. x4 equals 2 t plus 3. And x5 is simply equal to t. And that's my parametric solution. Okay? Now x is going to equal s times, and notice there's no s's anywhere except for x2. So that's 0, 1, 0, 0, 0 plus t times, and now this is going to be 2, 0, negative 1, 2, 1. And there it is. There's our parametric solution. Oh, wait. And then plus, we've got a remaining vector here, which is just a constant vector. So that's going to be 1, 0, negative 1, 3, 0. Because you notice you've got 1 right here, negative 1 right here, and 3 there. Okay, cool. Now, write the solution AX equals 0. What we want to get is that AX equals 0 is going to look identical to this particular one, or its row reduction. The row reduction of A does not change, right? So the row reduction of A does not change no matter what value we have, no matter what B we have, right? See, this is B. And so in this case, if I row reduced AX equals 0, what I would get is I would get this. 1, 0, 0, 0, negative 2, 0. 0, 0, 1, 0, 1, negative 1, 0, 0, 1, 0, 0, 0, 1, negative 2, 3, and then 0, 0, 0, 0, 0, 0. Lots of zeros, okay? Now, what that would mean then is we'd basically just write this all out. It turns out, not negative 1, it's just a 0 there and a 0 there. Sorry, my bad. Zeros all the way around. Zeros all the way down in the augment. What that means is that we're actually going to end up with this exact same solution. You can kind of check it out. You're going to end up with your parametric solution. X1 is just going to be 2t. X2 will just be an s, right? It'll be free still. No pivot there. X3 will just equal negative t. X4 will just equal 2t. And X5 will equal t. Okay? So now I have x is going to equal, right, s times this vector, 0, 1, 0, 0, 0, plus t times 2, 0, negative 1, 2, 1. So I still have a plane as my solution, right? I've got the same plane as my solution. It's just, excuse me, I still have a plane as my solution. It's just not the same plane. This plane goes through the origin. This plane up here goes through 1, 0, negative 1, 3, 0. But they're planes, right? If we imagine, right, these two planes, they have the same slope. It's just one is, kind of somewhere else in space, right? They're parallel planes. And on the one hand, you've got this one that's going through the origin. And then on the other hand, you have this one up here that is not. Okay? Now, is AX equal B consistent for all values of B? And the answer is no, it is not. Take a look here, right? We have a row of zeros down here on the bottom, right? Since the rank, there's a theorem that we talked about. Since the rank of A is equal to 3, and the rank of the augmented matrix, right? The rank of A hashtag could be 4. This means it's possible that AX equals B could be inconsistent. Basically, that row of zeros indicates that given the right vector, if I find the right vector, I'm actually going to end up with that 0 equals 1 situation. right? Because I've got that row of zeros, it's possible that I can find a vector that is actually going to end up giving me no solution. So consequently, ax equals b is not consistent for all values of b. So just to finish things off, don't forget there are a lot of different ways to think about each one of these problems. Some of them, it's a foregone conclusion. Write the solution to ax equals 0. There's only one of them, right? Write a parametric and vector solution to the system. There is a right way to do that, okay? But this question, is ax equals b consistent for all values of b? The answer is no. It's always going to be no. But how you explain it might be a little bit different. You might say something like, I gave a rank argument. I said the rank of A equals 3, and the rank of A star, or augmented one, could be 4. And so since those two are different, that means that we could have an inconsistent system, right? But there are other ways to talk about this too, okay? You might make the statement, that I don't know, that since you have a row of zeros, we could end up with 0, 0, 0 equals some value if we're given the right vector b. Okay. At this point, that's kind of like, it's a pretty good explanation because at least it shows, hey, I know what's going on. When I look at a matrix, I understand the coefficient matrix row reduces to this. This tells me that ax equals b does have unique solutions, or it'll tell me that ax equals b does not have unique solutions for all b. Right? I mean, it's just one of those things. That's what I'm trying to like get at. Is I'm trying to understand what you understand about matrices when you look at them and you analyze them. What does it say about the systems that you're looking at? What does it say about the coefficient matrices? Right? Okay. And that's what I'm really trying to get at. Okay. So just make sure that your arguments are correct. And if your arguments are correct, right, and they apply to the the correct ideas, right, then you'll be fine. You'll actually do quite well here on this exam. Okay? That ends the video.